Hello, everyone. So then in this particular video, we're going to go and talk about the coordinate theorem, which is the way to go and connect concepts we've already established are true in Rn with our general vector spaces. So then it goes like this. Suppose you have coordinates. You have a certain vector space and a basis for that space. Now, for any two vectors in that space and any scalar, if you ever want to know the coordinates of the multiple k times v, what you do is you find the coordinates for v and just multiply it by k. In other words, in terms of the operation to associate a vector with its coordinates, in that operation, the scalar can be brought outwards. If you want to know the coordinates of u plus v, you can instead find the coordinates of u and then find the coordinates of v relative to the basis b, and then just add them together. In other words, if you think about the operation that goes from a vector to its coordinates, that operation distributes through sums. And these are the two things we need in order to behave very well with linear combinations. Now, proving this is incredibly easy. It's a matter of just pushing symbols around. So I'll do it quickly. If you have a vector v and you expand it via the basis b to get the coordinates c1, c2 up to cn. If you then take k times v, you can just multiply k right through that linear combination to get k times v as a linear combination of the basis vectors. But that means then the coordinates of v relative to b is just the vector c1 through cn, and the coordinates of k times v relative to the basis b is k times c1, k times c2, all the way down to k times cn, and that's just k times the coordinate vector of v relative to b. And that's exactly the theorem. That's at least the first part. So then I could, of course, prove the other one doing the exact same kind of tricks, just comparing two different vectors on left and right, show that they're actually computationally the same thing. But what's important here is that these are the two operations we need to say that the mapping that goes from vectors to their coordinates distributes through multiplication, through scalar multiplication, and distributes through vector addition. Now, this then leads to the big bag coordinate theorem, which says that if you have a basis for a vector space, if you give me any vectors at all, v1 through vn from that vector space, then those vectors are linearly dependent if and only if the coordinates in Rn are dependent. The vectors are independent if and only if the coordinates in Rn are independent. The vectors span the vector space V if and only if the coordinates span Rn. This is great. This is great because that means we can talk, instead of talking about this weird general vector space, we can bring everything over to Rn instead, do our work there, and come back. That way we have the algebraic power of the theorems, but we don't lose the computational ability that we learned back in Rn when we were computing vectors in that space. This is fairly important, so I'll quickly prove it. It's very easy. So suppose you have a basis B for a vector space, and let v1 through vr be vectors in that space. Let's just suppose that they are dependent. I'm going to assume that these vectors v1 through vr are linearly dependent in the vector space V. That means there's a linear combination that's not trivial. So one of the scalars is not zero. So this linear combination adds up to the zero vector in V. Now that's reversible because that's just the definition of what it means to be linearly dependent. But then these two vectors that you see on either side of the equation, those are equal. So if those are equal, their coordinates must be equal. And that's because of the uniqueness of coordinate representation when you have a basis for a vector space. But then we remember that the coordinate operation as a mapping that goes from the vector space to Rn, that distributes through vector addition and through scalar multiplication. So then if that's true, this is true. And again, it's reversible. But then we also remember another fact, that the zero vector in V, its coordinates, is the zero vector in Rn. So then this means then I have just formed for you a linear combination of vectors in Rn. Remember, the coordinates v1 relative to b is something in Rn. So that's a linear combination of vectors in Rn. And that adds up to 0. And the linear combination is not trivial, which means, by definition, that those coordinate vectors are linearly dependent. And that's it. This entire argument is completely reversible. The reason this argument works is because coordinates are unique. Coordinates are unique for relative to a single basis. Okay, so let's just make sure you see how this theorem is great. Any question you have now in a weird vector space, you could drag it back over to Rn for some n and answer it there instead. So I'm going to show you that these vectors are linearly dependent. So why? So then the coordinates of these vectors relative to the standard basis E for P2 is, it's the set 1, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. But these vectors are dependent. These vectors are linearly dependent as there are 4 of them in R3, which is only dimension 3. So they're dependent. Therefore, the original set is linearly dependent also. So by the coordinate theorem, the original set is linearly dependent in P2. Neat, right? So instead of worrying about this weird vector space, we bring everything over to R3. And in R3, we know that if you have 4 vectors in R3, they're instantly dependent. Let's just do it again. These 3 vectors cannot span M22. This time I'll just talk it out. So then these 3 vectors have coordinates relative to the basis. Well, the basis for M22 is E11, E12, E21, E22. And notice there's 4 of them. That means then that the coordinates of these vectors relative to that basis are in R4. So I have 3 vectors in R4. Well, 3 vectors in R4 can't span R4. It's not possible because you need 4 of them. So then since the coordinates don't span R4, these 3 vectors do not span M22. That's it. That's the argument. Neat, right? Neat. So then we can actually generalize this argument so we don't have to keep going back to the standard basis and talk that way. So doing so, notice that the arguments I just gave you could generalize if you want. I'll do it just once. If you have a basis of n vectors for a vector space V, then if you ever have more of them, then they have to be linearly dependent. If you ever have less than n vectors, then it can't span the space. It literally is just reproducing the argument I just gave you, but symbolically. So doing it quickly, let's suppose you have a basis for a set of some kind. So you have a basis of n vectors for the vector space V. And now just assume that we have m vectors in that space. And m will be more than the n, which is the number of vectors in the basis. Well, then the coordinates of those m vectors would give you m vectors in Rn, because the size of the coordinate depends upon the number of vectors in the basis. Since there's n vectors in the basis, the coordinates are all in Rn. But then you would have m vectors in Rn where m is more than n. They're instantly linearly dependent. And if they're dependent by the coordinate theorem, well, then so is the original set. And that's it. That's the argument. Nice, right? I believe that's enough for that video.